Hi and welcome. I'm trying to learn particle physics, today missing dark matter, and after we've done it, we're going to do standing yoga. And if you participate in the standing yoga, please put it here on this. And this is the second part we're reading now. About 380,000 years after the Big Bang, the temperature of the universe dropped below about 3000 degrees Kelvin, making it possible for the first time for atoms to form. So 500,000 years after the Big Bang, the temperature dropped below 3000 degrees Kelvin, and now atoms could form. The transition from disconnected nuclei and electrons to electrically neutral atoms released a huge amount of energy in the form of light, and the expansion of the universe has since stretched this light to microwave wavelengths. There were disconnected nuclei and electrons, and they became electrically neutral atoms. They are saying that the nuclei were positive. And now when they connected together with the electrons, they became electrically neutral, because now the amount of protons in the nuclei equaled the amount of electrons on the outside, and that released a huge amount of energy in the form of light, and also, I don't think because of it, but also since then the universe is stretching. No, the universe is stretching, and that light which happened to be there emitted through the combining of electrons with nuclei with protons in them of atoms, so they become electrically neutral. Whatever I said at the start, it makes them to stretch them out to microwave wavelengths, this light. By studying the patterns of slightly hotter and colder patches in the sea and B, we have been able to learn a great deal about our universe's history and composition. So in the sea and B, wherever that is, there are hotter and colder places, and they helped to know more about the universe's history and what it is made out of. Among other things, these variations in the CMB. What is the CMB? Cosmic microwave background. Although we still can't see the stuff itself, we see evidence for dark matter everywhere we look. For example, in the radiation known as the cosmic microwave background. Radiation. Cosmic microwave background. Now, by studying the patterns of slightly hotter and colder patches in the cosmic microwave background, we have been able to learn a great deal about our universe's history and composition. Cosmic microwave background. Among other things, these variations in the cosmic microwave background tell us how matter was distributed throughout space in the early universe. So because we're not everywhere the same hot and cold, these little patches of cosmic microwave background radiation, it tells also how the matter was distributed in the universe. Because dark matter began clumping under the influence of gravity earlier than normal matter did, its influence can be seen in numerous small hot and cold patches, each covering an angle in the sky of 0.25 degrees or so. Why should they cover somewhere an angle? Dark matter had somehow more gravity or had stronger influence of gravity onto it, and it clumped earlier. And in the universe there are hot and cold patches, small hot and cold patches, and they have somehow an angle of 0.25 degrees. The pattern of these spots even allows us to determine how much dark matter must be present. Yes, so it's able to see just the amount of it and then to calculate up how much dark matter is there. It turns out that for every gram of stuff that we can see in the cosmos, there must 5 grams that we can't. So there's 5 times about as much. There's 5 times the mass of dark matter as of matter, basically, or 5 times, yes. of weight, whatever. But doesn't even include another, perhaps even more mysterious substance whose existence can be inferred from the cosmic microwave background radiation. Dark energy, a force that seems to be causing our universe to expand ever faster. A part of it is dark matter, which is 5 times as much of matter in it, where as it is matter there. There exists also dark energy, and that could be the region where the universe is not just expanding, but also expanding faster. Even if dark matter were needed to prevent galaxies flying apart, a supercomputer simulation suggests that the cosmos would look very different if it didn't exist. They are saying there's some areas where planets or something else are circling about something else, and if we calculate how much mass they have, they would, and see how fast they are circling, they would fly off. If an object, a planet with that amount of mass, so weighing so much, would circle so fast around another planet, according to physics, it would be too fast and would be flying away. The reason it does not is because there's this invisible dark matter additionally pulling in it, and the planet can spin so fast with so much mass because there is the additional dark matter pulling in it. And the whole cosmos would look differently if the dark energy wouldn't exist or something. No, it is necessary to keep the planets from flying away, basically. And also the universe would look differently if it wouldn't be there. These simulations track the movement of billions of particles through cosmic time with the aim of better understanding why the universe has ended up the way it has. So supercomputers are tracking the particles, are looking what is happening there. When atoms in a gas of ordinary matter are compressed, they collide more frequently. This interaction when gases are pressed together, they collide more frequently. Atoms are not still standing, they are flying around all the time. And if the room gets smaller, and they have to come closer together, they are colliding much oftener. If they collide, it makes at least sense that heat comes about. That would explain why if something is pressed together, it becomes warm. That would explain why a sun, if it has its gravitation, we're doing it in helium science, is pulling all the dust and it's falling into itself in faster and faster, and the potential energy is converted into kinetic energy. Why that star, that burning sun, is heating up? Because the gases, the big dust, interstellar gas clouds are pulled together, smaller room, they are bumping each other together, and heat comes about. And if there's in its sun more than 10 million degrees, in another book we read for hydrogen. These hydrogen atoms are pressed together, bumping together, are overcoming the electrostatic repulsion, forming helium, which has an outward force that holds the sun in an hydrostatic equilibrium. It is burning, emitting, whatever, also falling together, and the sun is burning. And the heat came about because the gases are pushed together, they have much less space left to bump into each other, or they're colliding much oftener, and every time they collide, heat arises. Something like that. That would make at least sense. This interaction tends to push the atoms apart and so hinders gravity from compressing the gas anymore. When atoms in gas of ordinary matter are compressed, they collide more frequently. This interaction tends to push the atoms apart and so hinders gravity from compressing the gas anymore. It is compressed, now we're bumping often together, and because we bump together, we're saying no, we still want to come out. We're bumping into each other, and it's not possible to make them closer together. Dark matter particles, on the other hand, interact with each other only feebly and so clump much more readily. I don't really know what feebly means. It means weak, I think. So they interact not so strong with each other, and therefore they clump easier. Whatever. They're meaning if they are pressed together, we are colliding faster maybe. Normally we're colliding faster, but that makes an outward force like on a TV thing where but it doesn't burn the screen in. It goes into the corner and then it bumps. So it bumps them together and it isn't possible to make it closer together. But it isn't so strong in dark matter. They don't interact so strongly with the bumping together. They can basically be pressed together and they clump. Simulations that embody these properties show that as the universe expanded and evolved, the first structures to form would have been clumps or halos of dark matter. I don't know what halos are. They say the first structures. They're saying structures in the sense of the first planet, the first stars, whatever exists, the first asteroids, the first things which existed were dark matter clumps. It was particle physics part. If you were here for particle physics, you can go directly to the next part of particle physics if you stay here and participate in the standing yoga. And that's where the angelsk. The feet are standing together, the reef in and lift the arms up. Out and down. In and up. Out and down. In and up. And out to the side. In and up. Out to the other side. In and up. Make an inch of space between the feet, open to the side. In and up on the tiptoes. Out to the other side and heels down. In and up. Out, sink down onto the heels. In and up. Out onto the side. In and up. Out and down. In and up. Out to the side. In. And down. Lean onto the knees. Breathe again in. And out, make a head of the back. In the middle. Out back. Inhale. Out back. Inhale. Out back. Breathe again in. Out, come back down the back, up at the top of the backwards shoulder. In the arms up. Come up on the tiptoes. And out and down, feet together. Breathe and bend your right leg. Out, stretch left leg. In change. Out, stretch your right leg. In middle. Out left. In middle. Out the right. In middle. Out and back. Breathe in, lift the right hand up. Bend the left leg. Look to the sky. Breathe out. Inhale down. Out and down. Breathe in, hand up, left hand. Light knee bending, look to the sky, breathe out. Inhale down. Out and down. Make a hand with space between the feet, shift the weight to the heels, breathe in, cut out. Out and up. In and down. Out and up. Take hold on the elbows and gently rock them side to side. Feet together, relief and straight back, halfway up. Out and down. In halfway up, straight back. Out and down. And in the arms again, up, hands to touch. Relief in the arms up. Out, lean back, draw the elbows together. In and up. Out and back, draw the elbows together. In and up. Lean with closed hands back. In and up. Out and back. In and up. Out, lean to the side. In and up. Out to the other side. In and up. And intertwine the fingers and reach high. Breathe out to reach in front of the back. In and up. Intertwine the other way around. Out in front. In and up. Out, lean back with long arms, draw the elbows together, bring the elbows down. In and up. Out, lean back with long arms, draw the elbows together, elbows down. In and up. Out, back with long arms. In and up. Out, back with long arms. In and up. Out, the hands down. In the hands up. Out and down. In and up. Out and down. And in a bit more explosive up. Out and down. And the last time, bring your hands to touch and lower them down to heart center. That goes for standing yoga. I thank you very much, and until next time.